So welcome back to the lecture on aerodynamics, right? So today we will discuss about a review of vector relations, right? So in the aerodynamics is actually full of quantities that have both magnitude and direction. For example, if we consider any force, velocity, and so on. So the vector quantities are the very important mathematical representation, right? So which can express various things in aerodynamics, and hence we should learn about the vector relation. I am sure many of you are familiar with the vector analysis. So I will just go through and it will be a refreshing class. So I start with okay. So the fundamentals of aerodynamics by John D. Anderson, I acknowledge, right? Yeah. So let us start with the review of vectors, right? So in the review of vectors, we already consider a vector quantity A, right? So let us say the vector quantity A, both having magnitude and direction, right? And we can call something like this A. This is the absolute of A. This is a vector, right? And say if we consider the absolute of A will be a scalar quantity that you know, and somewhere we mention n is a unit vector, right? So let us consider n be the unit vector, right? So usually the unit vector is defined as A by the magnitude of A, right? So we consider this as a unit vector n, right? And its direction also equal to that of A. So let us consider A be the vector. And again B, say let us consider the vector addition. So this is a vector A and consider that there is a vector A and B. Now for vector addition, we can write A plus B is equal to C. Now let us consider in the other way, the vector subtraction. So A minus B is equal to D. Okay. Now scalar product. So let us consider the scalar product, right? So A is a vector and B is another vector. So A dot B can be represented by modulus of A and modulus of B cos theta, right? So it means that magnitude of A into magnitude of B, right? And the say it is in along the direction of A. So the dot product or the scalar product we can consider A dot B is equal to modulus of A and modulus of B cos theta. Then let us consider a cross product, right? So we have A vector and B vector and the G vector, and this is almost we can consider the right hand rule. We consider G is perpendicular to the both the fingers, right? So the G is almost like we can have an analogy of thumb is perpendicular when we consider a right hand rule, right? So A cross B can be represented as modulus of A, modulus of B sine theta into E, that is equal to G. G is perpendicular to both A and B. So if you have a further question on this, I recommend you to refer your basics on vector, right? Now, let us consider the coordinate system. So you know very well to describe mathematically the fluid flow in 3 dimension. So 3 dimension, we need to specify the coordinate system, right? So for example, the geometry of any aerodynamic problems, if you consider, that may fit in rectangular space, right? So others in cylindrical nature and other may be in a spherical nature. So whenever we consider we have a Cartesian coordinate system, cylindrical coordinate system and the spherical coordinate system, right? So here let us consider this Cartesian coordinate system, right? We have x, y, and z, right? Or three axes and which are mutually perpendicular to each other. And the corresponding vectors, say I, j, and k, are the unit vectors in x, y, and z direction respectively, right? Now, let us consider any arbitrary point P. Any arbitrary point P which can be represented in x, y, and z, right? So we need to represent this, right? Anyway. So this point also can be located by a position vector r, right? From the origin, right? So now we have the position vector r, which can be represented as xi plus yj plus zk. Okay. Now let us consider this point P, right? So we consider A as a given vector and it is in the Cartesian space, and we have AX, AY, AZ are the particular vectors in that I, J, K. Then we can write A as A is equal to AX, I, AY, J, and AZ, K. Now let us consider the cylindrical coordinate system. Cylindrical coordinate system, please note, we have x, y, right? We have x, y, and then we have theta, right? So initially in the Cartesian coordinate system, we have x, y, and z. And in the case of the cylindrical coordinate system, right? We have r, right? We can represent r, theta, and we have z. So let us consider this theta, then consider P as a point which can be represented by P is represented by r comma theta comma z, and theta is the angle made from x-axis to y-axis in the xy plane, right? So if you want to represent any point P, you can represent in terms of r, theta, and z. So please note r, then theta, and this direction is z. Then let us consider A is having AR, ER plus A theta, E theta plus AZ, EZ. So here, if you want to represent X, the X can be considered as R cos theta, and the Y can be considered as R sin theta, and Z is Z, right? So R can be taken as x square, root of x square plus y square, and theta can be represented as tan inverse of y by x. And Z can be represented directly as Z. Now, in the spherical coordinate system, right? So, spherical coordinate system, we can represent r, comma, theta, comma, pi, right? So, here we have represented r, comma, theta, comma, z in the cylindrical coordinate system. But in the spherical coordinate system, we can represent anything in r, theta, and phi, right? So let us consider this case where we have r, theta, and z pi component. So how about x? X can be represented as r sin theta, right, and cos phi, right? So if you want to represent the x can be represented. We can represent the x by r sin theta and cos phi. Similarly, y also can be represented by r sin theta, right? R sin theta and sin phi. And how about z? Z is directly r cos theta, right? So P is the point which can be represented by r, comma theta, comma pi. So the resultant, okay. So as I said, x can be represented by r sin theta cos phi, and y can be represented by r sin theta sin phi. Now z can be represented by r cos theta directly, right? This r cos theta. So r can be represented by x square plus y square plus z square in the root, right? Again, theta is equal to cos inverse of z by r. So once you have z and r can be represented by root of x square plus y square plus z square, and pi can be represented by cos inverse of x by r. So x by root of x square plus y square. Right. So this is the simple information about the cylindrical Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Please remember that the Cartesian coordinate system we are mentioning x comma y comma z, and the cylindrical coordinate system we mention again x y z in terms of r comma theta comma z. Then spherical coordinate system we represent it by r comma theta comma phi. So any geometry can be represented by all these coordinate systems, right? Okay. Now we will discuss about scalar and vector fields, right? So a scalar quantity given as a function of coordinate space and time. So what is space? We have x, y, and z is space, and the time t, right? So for example, if we want to express the pressure, density, temperature, which are naturally the scalar quantities, we can represent by this way. Say P is equal to P1 of x, y, z, and t. That is Cartesian coordinate system, right? Similarly, the P can be represented by cylindrical coordinate system, that is r comma theta comma z comma t. Similarly, it can be represented by spherical coordinate system, right? So the pressure, density, and the temperature can be represented by Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system by this way. Now let us consider an velocity vector, right? This is a scalar field, and here we have a vector field, right? So a vector quantity given as a function of coordinate space and time. As I said, the space x comma y comma z and time is t. So a vector quantity given as a function of coordinate space and time, then we can call that as a vector field. Say for example, velocity is a vector quantity, and we can write velocity v is equal to vx, vy, and vz, right? And vx can be represented as vx of x, y, z, and t, vy as vy of x, y, z, and t, and vz of x, y, z, and t, right? So this is about the scalar and vector fields. Now let us think about the scalar and vector products, right? So let us say the coordinate system. we consider the coordinate system as Cartesian coordinate system here. And let us say A is a vector and B is a vector. So A vector is defined as AX I plus AYJ plus AZK. Similarly, B can be defined as BX, BY, and BZ. Right? Now, A dot B, right? So this is the scalar product. Can be represented as AX, BX, AY, BY, and AZ, BZ. Right? Now, how about the cross product? A cross B. Right? So if you want to represent this A cross B, you can represent in this form, right? And we can write this as I into AY BZ and AZ minus AZ BY. Similarly, J can be represented by AX BZ minus AZ BX. Similarly, K we can consider, right? So we can write in this form for Cartesian coordinate system. Now let us consider the cylindrical coordinate system. So in the cylindrical coordinate system, as we know, we represent R, theta, and Z. So A vector can be defined and B vector can be defined, and their scalar product, that is AR, BR, A theta, B theta, and AZ, BZ. Again, in the cylindrical coordinate system, we consider A cross B can be represented by ER, E theta, EZ, and then AR, A theta, AZ, and BR, B theta, BZ. And you can expand later, right? Now, we can go to the spherical coordinate system. Only difference is R, theta, and phi, and we can represent A dot B and A cross B, right? So this is about the basic information on the vector relation, right? Now, we also should remember that in aerodynamics, we represent most of the things in the mathematical form, right? So we represent in mathematical form so that anyone can understand it, right? Okay. The next concept is the gradient of the scalar field, right? So we have, let us consider a scalar field where there is a pressure P1 of x, y, z in the Cartesian cylindrical and spherical coordinate system. We have, say, let us assume in a xy plane, it is a two-dimensional plane, right? Ultimately, we want to calculate the gradient of P. The gradient of P is represented by this inverted del P, right? Now, the gradient of a scalar field we want to say, right? Now, in this xy, if you consider P1 is constant, P2 is constant, and P3 is constant. Here, the P1, say this P1, it considers the pressure, the same pressure at all the points, right? Then you draw a line and you say that that line where P1 is constant. Similarly, P2. Okay. Similarly, P3, you can draw a line. This line, it is not necessary that it should be like this. It can be of any pressure, but only thing is the pressure along that particular line is constant. And then we call that as isolines of pressure, right? So let us say P3 is greater than P2 and then P2 is greater than P1. That will be the basic point, right? So now there is a gradient lines, right? We want to talk about the gradient lines. I told you it is in the case of calculation of forces, moments, and all those things. We always consider the pressure difference, right? Whenever there is a question on aerodynamic force, two things are involved. One is skin friction and another one is pressure, right? So pressure, we have made a discussion that the flow will be from the high pressure region to the low pressure region and so on. So assume that if there is a pressure and there is a difference in pressure and there is a gradient line, right? So the direction will be in such a way that it will be having the low pressure, high pressure, and based on that there will be a direction. But the direction of flow we can represent in terms of gradient lines. So here we need to note that the isolines and gradient lines are perpendicular to each other. What is isolines of pressure? The constant pressure region, right? The constant pressure lines. And the gradient lines, the gradient lines are perpendicular to the isolines, right? So we can say that the gradient of P, that is del P, at a given point in a space can be defined as a vector such that its magnitude is the maximum rate of change of pressure per unit length of the coordinate space at the given point of time. And its direction is that of maximum rate of change of P at the given point, right? So this is what the gradient of P. Now let us consider del P at a given point X and Y, right? So let us say this is a point X and Y, and let n be the unit vector in the direction of S. So the rate of change of pressure P with respect to S direction can be represented by del P dot N, right? So the pressure dP by ds can be represented in terms of del P dot N. So what is dP by ds is called the directional derivative in the S direction, right? So the directional derivative in the X direction. And only thing we need to remember is the expression for del P. How can we represent the gradient of a scalar field, gradient of the pressure? So the gradient of the pressure, this is the symbol we use for a gradient, and P is pressure and gradient of pressure. So the rate of change of P in any arbitrary direction is simply the component of del P in that direction. So now, as usual, we know that we have P of x comma y comma z is for the Cartesian coordinate system, and similarly r comma theta comma z for the cylindrical coordinate system, and r comma theta comma pi for the spherical coordinate system. Now, how about representing the del P? So the del P can be represented by dou P by dou x in I and dou P by dou y j plus dou P by dou z k. So this is del P. We will do some problems later on calculating the gradient of a particular field, right? So this is the information we need to know. Now let us go to the cylindrical coordinate system. R, comma, theta, comma, z. So we can represent the gradient of P as dou P by dou R into ER plus 1 by R into dou P by dou theta into E theta plus dou P by dou Z into EZ. Similarly, the spherical coordinate system can be represented. See, I have mentioned in the previous discussion when we consider the spherical coordinate system, cylindrical coordinate system, and the Cartesian coordinate system. Here you see in the Cartesian coordinate system, you have x is x and y is y and z is z. In the case of Cartesian coordinate system, cylindrical coordinate system, x is r cos theta, y is r sin theta, and z is z. And in the case of spherical coordinate system, x is r sin theta cos pi, y is r sin theta sin pi, and z equal to r cos theta. And hence, whenever we go to the gradient field, gradient of a scalar, we have the Cartesian coordinate system, and here we have a cylindrical coordinate system and the spherical coordinate system represented in terms of r, theta, and pi. Right? So the gradient of a scalar field. Before that, what is gradient? The gradient is because of the flow of fluid in the direction of the pressure difference, direction of maximum change, right? So if you want to represent at any point x comma y, we can represent in terms of del. That is what the concept, right? Every time when we think about a gradient or divergence or curl, you should always remember the physical significance of that particular term, right? Now, we will think about the divergence, right? Now, let us consider a fluid element. The fluid element moves through the space, right? So when the fluid element moves through a particular space, I hope you remember the flow field we have done some times back when there is a flow, and we have made one small fluid element, right? And the fluid element moves at a particular velocity, right? The fluid element moves at a particular velocity can be represented by v, x, y, and z. Since it is a vector, we can represent this nicely in x, y, z, r, theta, z, and r, theta, pi in the case of the respective coordinate systems, right? So, now I want you to visualize. I told the fluid element moves through this space. Its volume may change. The change in volume of the fluid element, it may increase or decrease, but there is a possibility of change in the volume. Our ultimate goal here is to represent the change in volume. So, we like to prove that the time rate of change of volume of a moving fluid element of fixed mass per unit volume of that element is equal to divergence. Now you understand the mathematical point of studying aerodynamics, because the divergence of the velocity can represent the time rate of change of volume of a fluid element of fixed mass per unit volume of that element. So it is a wonderful information. Change in volume of a fluid element can be represented as divergence of V. Divergence of V is nothing but the change in volume of the fluid element, right? So here we can represent the divergence, right? So divergence of a vector is a scalar quantity that we need to note, right? So it is one of the two ways that the derivative of the vector field can be defined. One way is divergence and another one is curl. curl we will study next, right? So I hope you understand the physical significance of divergence. I want you to check in the dictionary what is the English meaning of divergence, and you will get a good idea, right? Now, let us express again in terms of Cartesian coordinate system. V of x comma y comma z. We can write Vxi, Vyj, and Vzk, and the del dot V, that is divergence of V, can be represented by dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z. Now, we can represent the same divergence in the cylindrical coordinate system. In the cylindrical coordinate system, we know r, theta, and z, and we can represent del dot V as 1 by r into dou by dou r into r Vr, 1 by r into dou V dou theta plus dou Vz by dou z. So this is the expression of divergence in terms of the cylindrical coordinate system, right? Now, we can represent again in the spherical coordinate system. I recommend you to visit the book, and you can also arrive to this particular point, del dot B. So we know that the divergence of a vector field. What is divergence? The divergence is a simple representation of time rate of change of volume of a moving fluid element of fixed mass per unit volume of that element, right? So please always remember what is divergence, what is gradient, and next point, what is curl, right? So the curl of a vector. The curl of a vector can be represented in, again, Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. I will tell you the representing anything in terms of Cartesian, cylindrical, and spherical will be very useful when you go for doing a geometric modeling in the SolidWorks, CATIA, or even ANSYS, something like that. So you can represent nicely, right? So here the curl, say the omega, right? We consider here the omega is equal to 1/2 of the curl, right? What is omega? Omega is actually the angular velocity. The angular velocity omega, right? So the omega can be represented by 1/2 of the curl of V, right? The curl can be usually denoted by del cross V. So we can represent nicely. So what is the meaning of curl? It is like if you visualize any fluid element, the fluid element will be rotating, right? The fluid element moves, right? The fluid element moves, that we have discussed in terms of gradient. The fluid element, the volume changes, that we have discussed in terms of divergence. The curl, which discusses about the rotation of the fluid element. So the rotation of the fluid element will be having an angular velocity, right, as it translates along the streamline. Say, for example, if you consider the fluid element moving in a fluid flow, say this is the fluid element. In the divergence, we have discussed that this volume may change. The rate of change of volume we have discussed. Here, let us say the fluid element, say now the fluid element will be like this. And now here, if you consider the fluid element may be like this. So it discusses about the rotation of the fluid element. So here we prove that the angular velocity is equal to 1/2 of the curl, where curl can be represented by del cross V. Okay. The curl of V is a vector quantity, and it is the alternate way that the derivative of a vector field can be defined. The first is being the del dot V. So del dot V and del cross V are the two important components where we can represent the fluid element, right? So let us think about the curl of the vector. The curl of the vector in the Cartesian coordinate system, we can represent V is equal to Vxi, Vyj, and Vzk. Then we can write del cross V in the form of matrix Ijk and dou by dou x, dou by dou y, and dou by dou z. Then Vx, Vy, Vz. So this can be further written as I into dou by dou y of Vz and dou by dou y of Vz and dou by dou Vy by dou Z plus J. When you consider J, you need to consider this. So dou by dou x of Vz and dou Vx by dou Z. Dou Vx by dou Z and dou Vz by dou x. Similarly, the K can be considered with these two terms where K is equal to dou Vy by dou x minus dou Vx by dou y. So this is the representation of curl of a vector in Cartesian coordinate system, right? Then cylindrical coordinate system. Cylindrical coordinate system, you know very well, we have r, theta, and z. So we can represent del cross V is equal to 1 by r into er, e theta, e z, and dou r, dou theta, dou z, and all these components we can consider. Similarly, the spherical coordinate system. Spherical coordinate system we can represent in this way. I recommend you to do this exercise by yourself. And finally, you can arrive to 1 by r square sine theta into the representation er, e theta, and e phi. So these are all the information we had for this basic review. So please remember, we will revisit it once again from the starting. So in the starting, we considered a vector A, then we considered two vectors A and B, and then we have considered the vector addition, vector subtraction. Then we note that the scalar product can be expressed as A dot B, and similarly the vector product can be represented as A cross B. And we denote a unit vector n, in some location we have mentioned as E, and so on. So unit vector can be represented by this way. So we start with the Cartesian coordinate system. In any Cartesian coordinate system, see, it is not that something different where, say, P is a point in any space. This P can be represented by any one of the coordinate system. So here we have represented P in x, y, z, and in the cylindrical coordinate system we express this r comma theta comma z, and r comma theta comma phi is the representation in the spherical coordinate system. And then the corresponding x, y, z, r, and the theta values we have discussed, right? So here we have r, theta, and pi, and the x, y, z. We have a different notation, right? Then here we start with the scalar field, where the scalar field in space and the time can be expressed. Say the quantity pressure P can be expressed as x, y, z, t in the Cartesian coordinate system. In the cylindrical coordinate system, we can represent it in r, theta, z and t. Similarly, the spherical coordinate system, we can represent in terms of r, theta, phi and t. So vector field, again vector field can be defined in this way. V is equal to Vxi plus Vyj plus Vzk, and Vx is in terms of space and time, right? Similarly, Vy and Vz. Then we have discussed about the scalar and vector products, right? And again, we have discussed it in the cylindrical coordinate system, Cartesian coordinate system, and the spherical coordinate system. Then we move to a point called gradient. I told you we have isolines P1, P2, P3, and usually for the GATE exam they ask one question in this gradient, divergence, and curl. So you need to study, you need to read it little deeper, right? So gradient of a scalar field can be represented by del P, and del P can be represented finally by dou P by dou Xi plus dou P by dou Yj plus dou P by dou Zk. Similarly, in the cylindrical coordinate system and spherical coordinate system. Then it comes the divergence. You know that the divergence is the divergence of the volume of the moving fluid element. That means the time rate of change of the volume of the fluid element in a fixed mass per unit volume of that element is expressed in divergence. However, the curl can be represented in terms of the rotation of the fluid element in terms of angular velocity. And we have the discussion that the omega usually represented as 1/2 of the curl of V, that we will discuss, right? And the representation of curl can be done in del cross V. So Cartesian coordinate system, cylindrical coordinate system, and the spherical coordinate system. So that's all about the review of the basics. And in the next class, we will discuss about the surface integral, line integral, surface integral, volume integral, and its relation, and also the various fluid models, right? And we will be, progressing one by one in the aerodynamics. Thank you very much. I stop at this point.